Hey everybody, welcome back to another round of astronomy, and yeah, let's get at it. I have a question for you to start off with. So here it is. You wish to study the birth, life, and death of a sequoia. Okay? Now, I would like you to articulate two different ways that the birth, life, and death of a sequoia could be studied. Yeah, you got it? Yeah, good. So let's go ahead. And I imagine that probably the first way that you came up with is something like this. Let's take a seed, we'll plant it in the ground, and we'll watch it grow. We'll watch it bloom and become a little sapling, and watch that sapling become a full-grown tree, and eventually watch that tree die, fall over, and we're done. Okay? Now, there's an issue here. If you're familiar with sequoias, and there's a reason why I chose sequoias in the first place, some of the oldest sequoias live to up to 3,000 years. Whoa. Okay. So the question then is, how in the world can we study the birth, life, and death of a sequoia when a sequoia lasts for so long? There's got to be another way. Yeah, you probably already identified it. Rather than studying a single sequoia and watching the birth, life, and death of a single sequoia, the other way that we could do this study is let's find a group of sequoias, a forest. And by studying a forest, we can understand the birth, life, and death of a sequoia. We just have to find a forest with the sequoias at different stages of their quote-unquote lives. Okay? And similar to studying the birth, life, and death of sequoias, we're not going to be able to watch a single star and watch it progress through its natural life. Rather, we're going to have to find a forest of stars, and by studying the entire forest, we get an idea about how stars are born, evolve, and die. Now, how do we actually go about forming an HR diagram? One of the pieces of information that we are going to need is that we are going to need how luminous all of the stars are. Well, how do we actually go about getting that sort of information? And we remember from our rich uncle problem that the brightness of a star is the luminosity of a star divided by 4 pi, the distance to the star squared. And so if we rearrange that equation, we get 4 pi times the distance to the star squared times how bright the star appears to be. That will give us the luminosity. Okay? So we say, up until this point, what technique do we have to measure the distance to stars? Yeah, good, the parallax method. And as described in the parallax video, the parallax method allows us to measure distances to about 1,000 light years, 1,000 parsecs away, about 3,000 light years. So let's go ahead. Let's determine how many stars we can measure the distance to using the parallax method. So here's the question. What is the volume of a sphere with a radius of 500 parsecs? And you notice I have given you the geometric relationship. The volume of a sphere is given by 4/3 pi times the radius of the sphere cubed. So go ahead, take a minute and give me the volume of a sphere that has a radius of 500 parsecs. Yeah, good. You got it? Sweet. Nice. Okay, so we have the equation. All we have to do is substitute in the 500, and we're going to go ahead and cube 500. So, I don't know, 5 squared is 25, and then multiplied by 5 again is something like 125. There we go. And so we go ahead, we throw that all into our calculator, and we get a volume that is 5.2 times 10 to the 8th parsecs cubed. And you say, well, Greg, how is that going to help me out? Let's get to the next question. Okay? We are going to now make an approximation. Okay? So the approximation is this. We know that the distance from the sun to the next star, Alpha Centauri, is about 1.3 parsecs. Okay? Let us assume for a moment that that is the same distance to every star in space. In other words, on average, it is about 1.3 parsecs to each star in space. Okay? So here's the question for you. Okay? We know, we just calculated the volume of a sphere that has a radius of 500 parsecs. Okay? And let's assume for a moment that there is one star for every 1.5 parsecs cubed. Okay? Question for you. In this sphere surrounding the Earth, how many stars, ballpark, are contained within that sphere? Go ahead, see if you can come up with an answer. You got it? Yeah, good. Okay? And here, all we need is a simple proportion. Okay? We say if there's one star for every 1.5 cubic parsecs, 1.5 cubed parsecs cubed, then how many stars will fit into this volume? So we can take this, and we're interested in x, and if we go ahead and cross multiply, we'll notice that we end up with parsecs cubed divided by parsecs cubed. And that 3.4 is apparently 1.5 to the third. Okay. And so at the end of the day, we say, well, there's about 150 million stars, 150 million stars that we are in this sphere. A different way to say it is that there's about 150 million stars to which we can measure the distance to using this parallax method. Okay? So here's a quote for you. Okay? We can only determine the real brightness of a star when we know its distance. But the recent accumulation of direct measures of parallax put at our disposal far more extensive data than were available a few years ago. Now, a Hertzsprung-Russell diagram actually takes a couple of these ideas and puts them together. So we've already talked about using the parallax to get the distance, and then once we know the distance, I'll make that a D. Once we know the distance and the apparent brightness, we can then find the luminosity. Hertzsprung-Russell had a wonderful intuition that we're going to take the luminosity of the star and plot that on one of the axes of our diagram, the vertical axis. On the horizontal axis, as I've already hinted at, Hertzsprung-Russell decided to plot the temperature. So this is a really good point where we should ask ourselves, how do we get the temperature of distant stars? Yeah, you got it? Yeah, and this is where we have to go back and reflect. What do we learn about on light? Okay. We learn that you can infer the temperature of objects by looking at the peak of the black body spectra, identifying lambda max, and then applying what we know as Wien's law. Hertzsprung-Russell plotted these two quantities and obtained what is known as the Hertzsprung-Russell diagram, or as I've already used, the HR diagram. Luminosity on the vertical axis, temperature on the horizontal axis. Okay. Now here is the first Hertzsprung-Russell diagram published in 1914. And you'll have to excuse me. You'll notice that rather than temperature, they have plotted the spectral class, which we've already mentioned are related. And rather than luminosity, they have plotted, you could think of plotting luminosity or similarly the absolute magnitude. So this is their 1914 paper, and I lifted these quotes directly from the paper. So the first thing they say is, upon studying figure 1, several things can be observed. All white stars are bright, far exceeding the sun. And so that's this upper purple triangle. And all very faint stars are red. Okay? And then, in addition to that, they decided they would go further. They said, hey, aside from hot stars being bright and cold stars being dim, this trend that goes from lower right to upper left, the other thing they noted is up here in this red section, that there are many stars of great brightness, such as Arcturus, Aldebaran, and Antares. Okay? So they said either the red stars are really cold, or they're really cold and dim, or really, really bright. And there are no stars in between. All stars of classes K, 5, and M are either very bright or very faint. There's no in-between gap. Okay? Now, Hertzsprung-Russell didn't realize at the time that this upper right-hand portion are actually stars that are in the process of dying. So if we ignore that upper right-hand portion, the birth and life of a star is on this diagonal line. That diagonal line, that pattern that Hertzsprung-Russell first observed, is what was referred to as the main sequence. Same thing's being plotted here. You can think of the horizontal axis as being temperature and the vertical axis being the luminosity of the star. And the trend line is more apparent, partially because we're looking at a larger forest. And yes, you should be able to interpret and pull data from this diagram as well. So let me highlight some ideas for you here. First of all, the Hertzsprung-Russell diagram is not a linear plot. It is a logarithmic plot. Okay? So to give you an idea, the absolute magnitude, again, is an exponential kind of idea, and so it makes sense to do a log-log plot, number one. The other reason why we like the log-log plot is that it allows us to plot a large range of luminosities and still be able to keep it manageable in terms of aesthetic appeal. So the second thing, the horizontal branch, as I've already mentioned, the horizontal axes, you can either plot temperature or spectral class. Okay. So I've decided to, this example image I've drawn up so that you have both temperature and spectral class. But remember that oftentimes you'll see one or the other, but generally not both. Similarly with the vertical axes, okay, you will either see absolute magnitude or luminosity, but generally not both. And when you see luminosity, for example, it's generally given in terms of solar luminosities. Okay? So 1 represents a star that gives off the same amount of light as our sun. Okay? Whereas 100, that would mean a star that gives off 100 times more light than our sun. Okay? So right away, actually I should ask you this. Right away, based on this HR diagram, what is the spectral class of our sun? Yeah, you got it? Yeah, good. This is off a cuff question, right? So let's get an idea. If 1 is the same luminosity as our sun, what we can do is think about drawing a straight line. Okay, so there's 1. You can think of drawing a straight line, And our sun is in the main sequence currently. So if we had our sun on this diagram, it should be somewhere in this ballpark. Okay? So you can say, well, it might be like an F9 star, or it could be as low as maybe a K, I don't know, a K0, or maybe a K1 star. So somewhere in the range of an F9 all the way down to a K0. Now I'll have to do a flyout. I don't remember off the top of my head exactly what the spectral class of the sun is. But we do know that the surface temperature is around 6,000 Kelvin based on our Wien's law example. So we should be somewhere in this area. Some like maybe a G2 star. Actually, as we get closer, we're probably something like a G2 star-ish. Okay, so that's where we can get the HR diagram from, how we actually create the HR diagram. The other idea that we should talk about is what information can we actually infer based on this diagram? Okay, so let's get at that. What information can we infer from this diagram? And you notice already I have some labels in here. Something like giant stars or supergiant stars or white dwarfs. How can we get a qualitative understanding of why that's why? How do we know what physical size these stars are? Okay. Ready for it? Yeah, let's go at it. So here we go. Question for you. Okay. You have two stove burners on which you wish to cook a pot of spaghetti. Which stove burner will definitely cook the spaghetti faster? Okay? And be careful. I should point this out. Green is hotter than red. Okay? So I'm using the astronomy kind of ideas about colors, which means red is hot, green is hotter, and blue is even hotter than that. Okay? So go ahead, take a second. Which stove burner will definitely cook the spaghetti faster? Yeah, you got it? Yeah, good. Because the stove burners are the same size, you say, well, the stove burners are the same size. Okay. That means that the stove burner that is a higher temperature should cook the spaghetti faster. Okay. So same size, but higher temperature. Okay. That means it should cook the spaghetti faster. Or, in other words, it gives off more energy. Okay. Good so far? Okay. Next question. Same idea. Okay. Next question for you. Which stove burner will cook the spaghetti faster? And notice I say definitely. Yeah, you got it again, right? Of course, this time they're at the same temp, but larger, right? If it's at the same temperature, but the stove burner is physically larger, that stove burner should give off more energy and therefore cook the spaghetti faster. Okay. So you see that there's an interplay between how hot the stove burner is, how large the stove burner is, and how much energy the stove burner gives off. Okay? We're going to use the exact same idea as we did for the stove burners. It's just we're going to apply it to stars. So let me give you an idea about that. Okay? So for example, if a protostar and a star have the same temperature, which star has the higher luminosity? Hey, you got it? Yeah, good. And this is just practice reading the HR diagram. Sorry, I'm grabbing a ruler. This is just practice reading the HR diagram, but you can imagine, okay, well, let's pick a temperature. Let's say right here, okay? And you can think of drawing a line up through the diagram and saying, okay, well, at this line represents objects at the same temperature. And so we see that if it's a main sequence star, it has some luminosity. Let's see if I can actually draw it here. It has some luminosity right here. Okay? Whereas if it's a protostar, if I want to read off the luminosity of the protostar, I see that a protostar at the same temperature has a much higher luminosity. Let's go a step further. Okay? A protostar and a main sequence star have the same temperature, and the protostar is more luminous. Which one has the larger radius? You got it? Two stove burners have the same temperature, and one stove burner cooks the spaghetti faster. Which stove burner is larger? Yeah, good. You say the one that cooks the spaghetti faster. Okay? The one that gives off more energy. The one that is more luminous. Okay? So right away, we have an idea that objects that have the same temperature, the one that is more luminous has to be physically larger in size. So in an HR diagram, as we move upwards, we are moving from small to large in terms of physical size. Good so far? Yeah, okay. Okay, so how about this one? Let's get another idea. Another HR diagram for you. Okay. Here's another question. How does the size of star U, which I have plotted right there, compare to the size of star X? Go ahead, pause the video, take a minute, see if you can come up with an answer. You got it? Yeah, good. So again, let's have an idea. Because you notice now star U and star X are at different temperatures, right? They're at different temperatures, but they have the same luminosity. Cold stove burner and a hot stove burner, but they cook the spaghetti at the same rate. Which stove burner has to be physically larger? Yeah, you got it, right? It has to be the colder one. The one that is colder has to be physically larger in order to cook the spaghetti at the same rate. Okay. So, how does the size of star U compare to the star X? U must be the smaller, physically smaller, and X must be physically larger. Boom, we're done. We now have an idea of why the corner of the HR diagram, as we go up and as we go to the left, we have an idea about why we label stars in that region of the HR diagram giants and supergiants. Conversely, as we go to the right and as we go down, we are getting physically smaller. And hence, we use the term white dwarfs. So that's at least one of the pieces of implicit information that's in the HR diagram. That stars in the lower right left are physically small. Stars to the upper right are physically large. Let me give you a couple more labels in here, just to give you an idea. There's some brown dwarfs. You see these pop up on the New York Times every once in a while. Brown dwarfs are what I refer to as the never were stars. They are they are clouds of gas in space that coalesce under gravity, but never actually become stars. And we'll have to talk about what distinguishes between being a star and not being a star. Okay? Then the next up are your main sequence stars. Okay? Those account for roughly 90% of all the stars we see in the night sky. So when you look out and when you look at a forest of stars, about 90% of them will fall along this pattern, this lower right to upper left sequence. Okay? And we'll spend next video asking ourselves why that is. Okay? Not only is it 90% of the stars, but basically they spend 99% of their existence on what we refer to as the main sequence. The giants and supergiants, Those are roughly about 3% of all the stars that we see in the sky. Okay? And these are stars that are in the process of dying. They are in the process of burning out. Again, we'll have to talk about what does that actually mean. The last percentage, because we say we can add 90 plus 3 is 93%. What are the other 7%? Those are down here in the bottom left-hand corner, called the white dwarfs. They are the stars that have completed their entire existence on the main sequence. They have completed their process of dying, and now they are sitting out in space, glowing embers, slowly cooling off. Okay? And that's where we bring in the death of stars. Okay, good. Well, I think that's enough information for this lecture. Keep working on the material, keep bringing questions up to class, and we'll keep discussing moving forward. But we're going to spend a couple more lectures discussing the HR diagram, and then we will start talking about how can we use the HR diagram as another measurement technique to see further into the universe. So I hope you're ready for it. Bring questions to class. Keep up the good work. I'll see you next time.